Okay, so I was saying something about this, right? Okay, 4.3. So we're focusing on analyzing the first derivative here. Tells us something about where a function is increasing or decreasing. And then concavity and flexion, this is focusing on interpreting our second derivative. So to start with, let's think about this problem of determining where a function is increasing or decreasing. So we kind of already have an idea of this already. We've seen that when a function has a tangent line with a positive slope, the derivative is positive. When a function has a tangent line with a negative slope, then the derivative is negative. So that tells us something about increasing or decreasing. So to be more specific about what we mean when we say increasing, we mean that the function values are getting larger as the function moves to the right. That means it's increasing. So something that looks like this. So we say f of x2 is greater than f of x1 whenever x2 is greater than x1. So that means that the function values are getting bigger as it goes to the right. Over here we have a decreasing function, meaning that the function values are getting smaller as it goes to the right. So in other words, f of x2 is smaller than f of x1 when x2 gets larger than x1. So it goes down, the function values decrease or get smaller as it goes to the right. Okay, so how does that relate to the slope? Well, we see here that when we have an increasing function like this, the slope of the tangent line is always a positive value. When we have a decreasing function like this, the slope of the tangent line is always a negative value. So we can test for increasing or decreasing by looking at where our function is, or where the derivative is positive or where the derivative is negative, right? So a function, so we'll say f is increasing for all x where f prime of x is positive, and f is decreasing for all x where f prime of x is negative. So that's the two key things that we're looking for here. Okay, so when f prime is positive, we know the function is increasing. When f prime is negative, we know the function is decreasing. And hopefully that kind of makes sense based on our understanding of what the derivative is. The derivative is related to the slope of the tangent. So a positive slope means it's increasing, a negative slope means it's decreasing. So let's just practice with a conceptual example here, sketching out a curve. First of all, the curve we're assuming is continuous, where it satisfies these conditions that the derivative is positive on these intervals from negative infinity to 0, from 4 to 6, and from 6 to infinity. So remember, this means that it's going to be increasing on those intervals. F prime is negative on the interval 0 to 4, so that means here it'll be decreasing on that interval. What does it mean for f prime of 0 to be undefined? Can you guys interpret what that means there?
But does that mean there's a vertical asymptote?
It could be, but I don't think that's necessarily what it means. It could be a vertical asymptote, but I don't think that's the case here because we're assuming it's continuous for all real numbers. So there's no points of discontinuity in the graph. So it couldn't
Okay.
be a vertical asymptote. What else could it be? So it's not a point of discontinuity, but it's a point where the slope is undefined. What kind of what kind of points have an undefined slope or have a derivative that's undefined?
Constant?
Say it again.
An equation, like constant equation? That's how you say it?
No, it's not. It's not a constant. Constant means that
Sine,
sorry. Go ahead.
sine, a
Sine.
sine. Yeah, the derivative of sine.
The derivative of sine. Well, not really. Sine is
Oh,
is differentiable always. So, okay, in this case, what this is saying here, f prime of 0 is undefined, is a point where it's not differentiable. We've talked about this, right? Yeah, it's like a point where there's a corner in the graph. Like there's a hard corner. So you can think of it like that, where we can think of here, f prime of 0 is undefined means there's a hard corner in the graph. So it's like there's a sudden change in the slope, where it suddenly changes from increasing to decreasing. So there's an abrupt change in the slope. And so there must be some hard corner in the graph. What about these points here where the slope is equal to 0? How do I interpret what those are?
It's just a straight line.
Okay, well, could you be more specific what you mean by that?
It's like the graph. Like if you were to graph it out, it wouldn't be either increasing or decreasing. It sort of remains constant. Or
Well, no, this is going to be a smooth continuous curve, but I'm asking what's going on at these points here at 4 and 6.
Is this like
The
the max?
derivative is equal to 0 at just those points. What does that tell you?
It crosses the x-axis.
Would this be the max?
Derivative does, but what does the original function look like there?
oh, it's like it's a like a. I don't know how to
So my suggestion is to think about what we did in the previous section. When we set the derivative equal to 0, what kind of points are we solving for there? What do we call these points? I know this was very recent. No, the original function does not have an asymptote because it's continuous, right? We're assuming it to be continuous for all real numbers. Okay, so okay, I'll just say it. So f prime of 4 and f prime of 6 are equal to 0, right? Those are just 2 points where we know the derivative is equal to 0. So these are critical points. 4 and 6 are critical points. Remember? That's what they are. We talked about this in 4.1, right? So we know they're local max or local minimum values. Okay. So we know, okay, let's put all the pieces together. We have f prime is increasing on these, f prime is positive, so f is increasing. The original function is increasing on these intervals. F prime is negative on 0, 4, so that's where it's decreasing on that interval. F prime of 0 is undefined, so there's going to be a hard corner there. This is actually, notice that this is also a critical point. So notice that here we also have a critical point. So it could also be a local a max or min. Okay. So that's important because now we want to think about it here. F prime of 0 could be a max or a local max or a local min, but it's got to have a hard corner in the graph. 4 and 6 are points where the slope is 0. So they could be a local max or local min, but we know they're just points where the graph levels out, right? Where there's a horizontal tangent. So that's really what we're saying here is that at these points, there's a horizontal tangent. Okay, so let's piece it all together. And the first thing I'll do is I'll just kind of put some points down at these key values at 0, 4. So we know it's got to be decreasing from 0 to 4. So I'll put the point down here, and then increasing again from 4 to 6 and from 6 to infinity. So, okay, so just kind of putting some random points there. So we know it's got to have a hard corner here. So it's going to have a sudden change in the slope there. It's going to have a slope of 0 here and a slope of 0 here. But then it's going to keep increasing. So actually here, let me draw that better so it's a little bit more exaggerating kind of what I was saying there, that here it's got to have a hard corner, so there's going to be a sudden change in the slope there, right? And then here it's got to change directions because it's going to go from decreasing to increasing. Here it's going to level out. It's going to have a slope of 0 here. But notice that it keeps increasing afterwards. So something like that. Or not quite that steep, but okay. So looking at those key things, right, that kind of agrees with everything. We've got it's increasing from negative infinity to 0, is decreasing from 0 to 4, increasing from 4 to 6, and then it continues to increase from 6 to infinity. We have here a hard corner at 0, so f prime of 0 is undefined. And then at 4 and at 6, we have horizontal tangents. So here at 4, we've got a horizontal tangent there, and at 6, we have a horizontal tangent there. Notice actually this is a local min. This is a local max. 6 is actually not a local min nor a local max because it doesn't change directions there. It levels out for a moment, but then it continues to grow. Okay, so anyways, this is an important kind of example that you guys should hopefully be able to do on your own. So I might give you something like this on an exam where I say, okay, here's some conditions, sketch a curve that satisfies those conditions. And you could have many different possible answers. But there would be, you know, a specific thing that I'm looking for, that it's increasing or decreasing on the correct intervals, that it's got a local max or a local min at those points, or maybe here it doesn't have a local max or min, but it levels out for a moment.